Welcome to SciFlux, the channel of scientific progress. We track the world's latest research so you can stay ahead, informed, inspired, and connected to discovery. Today we'll share the latest news inside the physics world. Imagine an electron drifting far from its atom, almost like a tiny satellite. These rare Rydberg states are crucial for understanding how molecules absorb light, but traditional models can't describe them well because they confine electrons too tightly. This study solves that by replacing standard atomic bases with plane-wave orbitals designed for these wide electron orbits. Then, an AI-driven method selects only the key interactions, reducing computation while keeping accuracy high. Tested on hydrogen, water, and ammonia, the approach closely matched experimental data and outperformed older methods. By removing artificial limits, researchers can now model Rydberg states realistically, a major step toward clearer, more accurate predictions of how molecules interact with light. On to the next breakthrough. Hydrogen could power a cleaner future, but it demands a huge pipeline network, and the weakest link may be the welds. The area around a weld, called the heat-affected zone, becomes harder and more brittle during welding. Under hydrogen pressure, this zone can crack, posing serious safety risks. To study this, researchers developed a smart workaround. Instead of testing full welds, they heat-treated steel samples to mimic the exact microstructures found in welded pipelines, from softer ferritic-benitic regions to much harder martensitic ones. They tested both modern and older steels, matching the hardness of real welds. Then, they ran fracture tests in air and under 100 bars of pure hydrogen. The outcome was clear. These welded zones lost major toughness under hydrogen, showing strong embrittlement and sharply reduced fracture resistance. The takeaway: weld microstructure is a critical vulnerability in hydrogen pipelines. Building a safe hydrogen economy will require tight control over welding practices and materials, right down to the microscopic level. On to the next breakthrough. In quantum mechanics, particles can cross barriers they shouldn't, a phenomenon called tunneling. It drives fusion in stars and even helps enzymes function. But most real reactions happen in asymmetric energy landscapes, and that's where traditional instanton theory fails. When the two sides of the barrier aren't equal, the math breaks down. Researchers have now fixed this by creating a new instanton framework using a projected flux correlation function, a smarter way to track tunneling between uneven energy states. They tested it on model systems and real molecules like alpha fenchol, and the results closely matched exact quantum calculations and experimental data. In short, it works where old methods couldn't. By extending tunneling theory to asymmetric systems, this breakthrough makes it possible to accurately model many chemical and biological processes for the first time, improving everything from reaction predictions to molecular design. Next up, rheology: how fluids deform and flow shapes everything from manufacturing to biology. To study this at the microscopic level, scientists often use dissipative particle dynamics, or DPD, but there's been a long-standing limitation. DPD only produced reliable results at very high shear rates, far from the gentle, realistic conditions where most real fluids operate. This new study fixes that. The researchers applied a technique called the transient time correlation function, or TTCF, which analyzes how particle interactions change over time instead of relying on long averages. By adapting TTCF to DPD, they sharply reduced uncertainty in viscosity measurements. The key breakthrough? Even at low shear rates, the signal quality stayed strong, meaning DPD can now accurately simulate fluid behavior under everyday flow conditions, without extra computational tricks. This unlocks much more realistic modeling of sensitive systems like blood flow, soft materials, polymers, and biological fluids. A smarter algorithm now lets us capture the subtle, real-world nature of how fluids move. Next up, another study pushing the boundaries. Let's move to the next discovery. Predicting how electromagnetic waves behave when they hit materials with very different magnetic properties is a major engineering challenge. This study tackles that problem using the time harmonic Maxwell equations, focusing on cases where the magnetic permeability contrast is extremely high. For example, when a wave moves from a magnetic metal into a non-magnetic material. The researchers proved uniform a priori estimates showing that the equations stay stable even when the boundary between materials is rough or complex. They also uncovered a clear pattern inside magnetic conductors. The electromagnetic field changes sharply near the surface, then rapidly fades deeper inside. This behavior can be captured through a multi-scale expansion. The outcome is a stronger mathematical foundation for predicting electromagnetic behavior in extreme environments. It directly supports the design of advanced shielding, sensors, and high-performance electronic components where large magnetic contrasts are unavoidable. Let's move to the next discovery. Next paper talks about how methane is a major driver of climate change, and leaks from oil and gas operations remain one of the biggest sources. Cutting these emissions requires continuous on-site monitoring, not occasional inspections. Researchers have built a practical solution: autonomous methane sensor nodes. These small, solar-powered devices can be placed directly at potential leak points. They're certified for hazardous environments, equipped with highly sensitive methane detectors, and use long-range LoRa communication to send real-time data from even the most remote sites. In field trials onshore and offshore, the system detected leaks as low as 1 gram per hour and measured emissions up to 100 grams per hour with high accuracy. Performance matched traditional inspection methods, but required far less manual work. This technology enables continuous, source-level methane monitoring, strengthening safety, maintenance, and environmental compliance. It's a critical tool for operators aiming to reduce emissions and move closer to net zero targets. Next paper talks about how. Next scientific work. Simulating hydraulic fracturing, where thick fluids crack rock, is extremely challenging because of huge viscosity changes and complex interactions. Researchers built a physics-informed neural network, or PIN, which combines AI with the laws of physics like mass, momentum, and fracture growth. Training on synthetic data and adaptive sampling, it accurately predicts what happens near fracture tips, where traditional models often fail. The results are impressive. Errors dropped by up to 90%. The model stayed stable even with noisy data, and it ran faster while using less memory. This physics-driven, mesh-free approach could transform subsurface modeling, helping optimize energy extraction and better understand how fluids and rocks interact deep underground. Next up, a discovery from a whole new perspective. For over a century, X-rays have been a cornerstone of medicine, fast, reliable, and widely available. Yet even today, scientists are discovering new ways they can help fight infections hidden deep in the body. A recent review traced X-ray evolution, from early film systems to modern digital detectors and CT scanners. Researchers explored how X-rays detect infections in lungs, bones, joints, and even fungal or viral diseases, and highlighted advanced tools like 3D imaging and X-ray microscopy for unprecedented detail. The takeaway? X-rays remain essential, not just for diagnosis, but for tracking disease progression, guiding treatment, and screening high-risk patients. With ongoing innovation, these classic tools continue to reveal the unseen and save lives. At last, what if your body could power its own medical devices? Imagine pacemakers or neural stimulators that never need a battery change. It's closer to reality than you think. Implantable medical devices are transforming healthcare, but power has always been a limitation. Batteries run out, requiring risky replacements. A new study explores multi-harvested self-powered systems, which tap the body itself for energy. Motion from your heartbeat or walking, body heat, and biochemical reactions can all be converted into electricity. The result? Fully self-sustaining implants that are biocompatible, always on, and never need recharging. Challenges remain, but the vision is clear. Smarter, longer-lasting, and truly sustainable medical devices powered by your own body. That's all for this video. If you want to stay updated with the latest scientific breakthroughs, don't forget to subscribe to SciFlux and join our newsletter for daily insights straight from the front lines of research.